All right. First off, I don't think still haven't quite gotten everybody's shares of their project. So let's do this. What I was going to do is sort of just to run through it to make sure. So here's a project that I have. I have enabled Collaborate on it. So File, General, Services, Collaborate has been turned on for the project. And I'm actually going to go to the Collaborate window here, or the pane, and I'm going to click on here and say Invite Teammate. And I have an alternate account on Unity. I'm going to use that to kind of step through it, just because. So here's my normal screen, and I'm going to invite via email. In this case, it's going to be eric@gmail.com. And notice it says also assign a Unity team seat to the server. So I'm going to go ahead and say add. And you'll see eric@gmail.com, Unity Teams, yes, user, and everything should be good. The other option is that all ORG users, I could be, let's see, if I already had an organization set up where this other user belonged to that organization, I could also share it with the organization, and then by virtue of that, share it as well. This is probably the simplest. You don't have to actually go through and associate me with a particular organization if you don't want that way. But so this is sort of the basic way to do it, just invite by email. So if all else fails and we can't get you there through the organization, we'll do it through email. So if after today I'm going to go through tonight, make sure everybody has, or whoever I can see, which I think was the majority so far, but there's still a couple and a couple of bumps. But before we get too far ahead on things, I just want to kind of go through that. So it should be as simple as that. So that should be that. We'll work our way through if you haven't already gotten there. Well, let's kill Discord here. All right. So here we are. We're at Wednesday there. So we're going to continue our intro to C#, syntax, variables, conditionals, debugging. Probably retrace a couple of our steps from last time a little bit. And then the second piece that we're going to discuss this week, Unity UI classes, functions, scene management, player preferences. It's really going to set up everything that you need for this sort of the simple room project. The idea with the simple room project is really, it's very little in terms of, there's no physics involved, there's no graphics per se, to worry about assets and animations, all that kind of stuff. We want to keep it really, really, really kind of simple. And basically, the second lecture, which I believe I already posted a link to, if you're already starting to work on the project, or you're concerned, or you're, in terms of what all the pieces are, you didn't quite get last time, we did show a little bit about, the audio sources and so on. It's not, I wouldn't say it's a step-by-step thing. In tomorrow, or however much we get to it today, lecture material goes, but there's a lot of it kind of covered in that second lecture, or the last lecture that's posted on LMS today as well. So there's a lot, all the techniques are kind of in there. So you should be in a pretty good position to kind of finish up the room before next week. If, depending on where we get to tomorrow And if we've covered everything, how I feel, there's always the chance that maybe we slide that deadline a little bit because I have compressed things a little bit. But we'll see. We'll shoot for that if we can stick to that. So let's go back to our C# programming in Unity. All right. And, so last time, I'm going to kind of really quickly go through the first couple ones because we're kind of at an accelerated pace. So I'm going to skip over a few things. Just review really, really basic syntax of C#. It's very, very similar to our other C family languages, even including things like Java, JavaScript a little bit, or our direct competitors to C, C++, C#. That whole class of things is certainly way different than something like Fortran or Lisp or something like that. But if you've studied esoteric computing languages, not that different from Pascal in a lot of ways. But it's these days, most of that sort of modern C family, the most basic function here, function name, and we pass the function arguments in our curved, or our normal curved parentheses there, and we finish a line with a semicolon. Important things, every statement ends in a semicolon, and things like white space, tabs, that kind of stuff are irrelevant. So we don't have structure or scope depending on how far in we're tabbed or anything like that, right? It's really about explicit things that are explicit in the code, right? We're going to always have scope delimiters, always have end-of-line delimiters, and so on and so on and so on. Within our functions or methods, our parameters will be passed in here. If we get a return value, it's only going to, one return value, generally from a function like this. So we could say function equal, or return value equals whatever the function name is. It's going to return a value like that, generally. It is an object-oriented programming language. A programming language does rely heavily on the use of things like inheritance and polymorphism and all of the wonderful object-oriented paradigms. So if you've taken any other course in Java or C++, all of the, for the most part, those basic concepts are all going to apply. We're not going to get into things about how good it is at garbage collection or memory management and things. Those are more computer science issues, and we're really, within game development, we do differentiate a little bit more between things that are scripting and coding, I guess. I know last time or first time in we said, oh, it's all it's all kind of under that same umbrella of we're putting things in a notation so that the a computer can interpret our intention and turn it into some result. But the notion of scripting versus coding, that's going to become, I think, a little less subtle as we go on, a little bit more, I don't know if it ever becomes really all that concrete, but we'll keep going from there. With regards to our purposes of working with a game engine, it probably is more, we're trying to get the engine to do things on our behalf as opposed to programming, whereas we'd be taking more explicit, responsibility for everything in the system. So maybe that's sort of one of the differentiations between scripting and coding, or scripting and programming. We're always, through scripting is usually some kind of other application or some engine that we're trying to get to do things for us. Whether it's even like Maya, if you're like doing 3D modeling in Maya, they might be using the Maya embedded language or things, some kind of scripting in there. So our coding is quite often scripting when we're working in programming languages. But we have all the kind of things that are wonderful about object-oriented programming languages in the C# language itself, kind of thrown in for good as well. So objects encapsulate some state and behaviors. So they generally have state inside of them or variables and properties inside them that they maintain that they are free to share with the world or protect from the world. They usually provide interfaces to those properties, interfaces or functions on those properties, methods on those properties to allow you to kind of manipulate their state or their functionality or their behavior in the world. So you normally wouldn't do things like set the velocity of an object. Well, we will wind up doing that. Usually you'll say move the object or something like that. So that usually we're going to want to think of things in terms of actions as opposed to directly manipulating data, in the theory at least, but we can violate that as we see fit. So we'll dive into that. Methods versus functions, properties, fields, attributes. Again, we're sort of abstracted a little bit at this point. We're not going to worry about too many of the fine points about, is that really should we be precise about saying what's a method, what's a function, what's a property versus a field versus an attribute? We can play a little bit loose with that. I am going to provide a very concrete use of getters and setters today, though, as a real demonstration of why some of these things may feel like more higher level, fancy features of the language, but they are there. They have great purpose and value to take advantage of them. So don't discount some of the more advanced features either. Right? There's some ways that hand in hand they can help us out as we're applying these things to game programming. Now, we're going to be dealing mostly with classes, meaning that one of the big differences is that, classes or objects, both of these things can contain functions and data, but normally structs are small objects spun up on the stack or, for small cases, whereas we're going to be usually dealing with classes. It's kind of the larger case, all our components are built as classes and so on. Now, I guess, since where we were last time, did everyone feel, did we go through, how much should I go through review this time versus last time? I guess we got up so far, we kind of summarized the language up to the point of kind of going through, and we quickly went through like operators, and kind of just viewed that as sort of a reference to a lot of these things. How, like it's always tricky to say, from people's backgrounds, how much step by step do people want or need, or at this point, if we make a statement like, something as simple as these assignment operators, right? You're sort of familiar enough with that sort of thing. Syntax is going to be really, at this point, most of these things are extensions of normal math practices and so on. I'd rather look at some of the structure of the language and syntax with regards to program flow. I think that's where it starts to become a little bit more divergent as opposed to statement by statement level. Right? So everyone's feeling pretty comfortable with the sort of idiosyncrasies of something like assigning the number 5 as an integer to a variable called x. Right? Should be pretty straightforward. The question then becomes, also, math. If I said, okay, you have y equals 10, x equals 5, and you wanted to do a multiplication or an add, saying, okay, this plus that, and an assignment, pretty straightforward. So that should be pretty simple. We have, of course, all our wonderful unary operators, for example. You can see these a lot. In CS1, does everyone wind up? You've all taken probably well beyond CS1 at this point. But things like unary operators, post-increment, pre-increment, post-decrement, pre-decrement, you're basically a way of saying, all right, this For example, classic C++ means add 1 to the variable C after it's been referenced. C minus minus, subtract 1 from C and assign it. So these are all kind of shorthand things. You could have said, just as easily said C equals C minus 1, right, that sort of thing, or C equals C plus 1. Unary operators, fancy things, are most of the time providing you kind of shorthands to things. Ternary operators, unary, binary, ternary, there's always like how many operators are there? There are 3 pieces. There are ternary operators where you do things like even say, all right, given a certain variable, you might conditionally set it to one expression or another expression. Now this is probably one of the more esoteric things, but it does lead well into, actual conditionals, right? So how many of you used a if, then, or if else in a program, right? Show of hands, everyone's going to be. For loop, right? Probably. For each, that sort of thing. All right, we got some pretty good coverage. So what I'll probably do is go through things quick for the majority and ask the minority if there is any subtle point that you missed. Ask me via Discord directly or things like that, rather than kind of painstakingly go through every detail of it, right? So, all right. So, I think last time we got up so far as to hint at getters and setters, and which were just sort of these special methods built into objects so that you could say, well, you could disguise a reference to a property in such a way that it felt like a direct reference to a property. You could say A equals B, and you wouldn't realize that instead of just an assignment, it was doing a whole bunch of extra things under the covers, right? So from a programming point of view, you would just say, okay, score equals score plus 1, and you would think, okay, I'm just adding to that, right? That feels like the normal, simple version of it. But getters and setters allow you to do things like sort of hide functionality underneath that interface, where you might say, okay, score equals score plus 1, and in addition to that addition and assignment, it would say, all right, also make sure that's drawn to the screen, right? Things like that, or make sure that it is within this boundary. Make sure it never goes negative. Make sure, in the case if it was a database, you might say, oh, if you ask someone for their phone number, you might say it's got to have a certain number of digits in it and can't have characters in it other than whatever, things like that. So there are some things that are definitely not obvious, but wind up hiding themselves under sort of the basic pieces of code and syntax there. So we'll leave that. I think that's a fun one to know about. If else is, of course, the basic, most flexible conditional in C#, and probably for the most part, I'd say other languages as well. It's definitely the most common one used. If something is true, then do something. It's easy enough to understand. If this is true, do that. If it's not true, do something else. Piece of cake. So, for example, maybe we have some sort of behavior for either our character or the state of the game, and we can look at certain variables to say, okay, if is daylight is true, so is daylight might be a Boolean value. Boolean values are allowed to be true or false. They can't have anything in between. There's no maybes to them. They're just true or false. So we'd say if daylight is true, or by comparing it to equals true, in that case, play the happy music, because it's daylight. Else, so we give it some alternative, and this is an else with an if, so it's not just the opposite of daylight being true. It might be a little bit redundant. So we said, okay, else if is night equals true, so we're checking to see is night true, then do some night stuff, right? Play cricket and owl sounds. So you might be thinking to yourself, well, isn't there just day or night? Why did you use an else if, or what's possibly going to be down here? You say, well, okay, it's not daylight, it's not night, then it means it's twilight or evening or dawn or something like that. So maybe we have some other conditions here, right? So if is daylight is true, that code ran, else that code would run, else the other code would run. So in no case would all three of these things run, right? We wind up with them excluding one another because they are completely contained if-else and if-else chain like that, right? We can have if statements within other if statements. So here, this is completely independent. It's just another block of code inside of there, right? Very, very similar. The big thing, very, very simple. The big thing to be aware of, syntax-wise, again, we're always using these curly braces to designate our scope. The tabs are arbitrary, but useful for readability of the code, right? There's lots of great debate. You'll see even in here, like a little inconsistent. Yes, it's absolutely inconsistent. Whether or not, say, this parentheses is after the line of code or on its own new line versus, say, down here where this curly brace is directly on the same line as that if statement. Wars have been fought over that sort of thing, right? You can get really, really bogged down in terms of which is the best way to do it. Are you trying to keep your code all on the same page, or are you trying to make it more readable, or who knows? There's lots of reasons to pursue one or the other. We could get carried away and have one statement per line, or one, whatever can be kept on its own line. That's what usually tends to happen. I make these sacrifices because I want to fit it all on the same screen. Does it still work? Is it the same? Yes. Right. So, if else, the most basic. We also have switch case statements. It's kind of the next alternative to something, or I should say, an alternative to potentially a more complex if statement. It's not, you can't replace every if with a case. That's certainly not possible. It's more when we're considering a specific value that we wanted to have code run based on, say, the day of the week. If you have one piece of code that runs on a Monday versus a Tuesday versus a Wednesday versus a Thursday, and you want to have a switch statement that can say, okay, depending on these exclusive cases, you could use that with this. But it's in many cases, you can replace some things that would have required a very, if x equals 1, do this. If x equals 2, do this. If x equals 3, do this. Right? Switch statements are a great way to just streamline that and just say, okay, let's consider x, or consider num up here, and then run this code if that number was 0, or this code if that number were 1, and so on and so on. Right? So it simplifies going through a bunch of different cases where a variable is equal to something. It can only compare for equality, so you can't use greater than or less than in there. Other complex conditional, it has to just be, okay, here's the number. It's more like using enumerated values. Right? You can compare only a single variable against literals this way. What happens if you leave out a break, for example? If the case has no body, execution will fall through. Otherwise, you get a compiler. What do I mean by that? You'll notice here, case 5 and 6 were the same. So say you have something where, even days of the week you do this, odd days of the week you do that. You could do something like that. But if I try to do this, print, whatever. Right. That's not allowed. I think you can get away with that in C++ and C, but you can't get away with that in C#. Right? The moment you have code for a case, it expects this to be, each case to kind of stand on their own like that. So this would have to be self-contained. Whoops, not brew. Interesting. Break. Right. It's a subtle point, but one to be aware of as you get into using case statements. The best thing, start off saying, well, okay, think of explicit cases. Don't get too fancy right off the bat. One of the strong things about case statements is you can also have a default statement. So here are all the things you want to deal with, and then here's the ones that you don't anticipate a specific value for. You don't care necessarily about these outlying conditions. You can just have a generic case to kind of take care of that. So that's another good feature, that there is a default case in addition to all the specific cases. All right. What's a trifecta, or in terms of, no, it's more than, there's like a classic structural pieces of any programming languages. Now we get into the loops, right? While and do while loops. Almost anything you can do with one, you can do with the other. It's sort of a question of optimization. Basically, when you want to have a loop run while something is true, or sort of until something is false, you can kind of do that all within a while loop. Execute the body of the loop repeatedly so long as a condition contained within the while is true. Right. So the typical, what we would say is a while loop would look like the one at the top here. While we would start off and say, immediately we'd have a check to say, while is alive, do everything inside of this loop, within these braces. The opposite, or the, I don't know, it's really an opposite, but the other version is the do while, where we say, okay, do at the beginning, and we have our while condition at the end. If we know that things are always going to happen at least once, we can use the do while loop as just an optimization to avoid potentially an unnecessary check. One of the reasons. So it's a question of, if we know, we want to allow for, at least one execution of the loop as opposed to checking the value on the way in. But, you can sort of do the same thing with either of them, except in the case that the do always has to run at least once. So, all right. For is the even more flexible version, because you can kind of do everything you'd want to do with a while loop in a for loop, depending on what parts you sort of leave out. Normally, a for loop is, we normally think of them as iterated loops. We're iterating over some number of values. Very often, you see this kind of common iterate from this number to that number. It's where fors kind of get their start, but you can use them in a lot of more fancy ways. Boy, my mask is really, it keeps it upside down today, I guess. But the classic for loop, for int I equals 0 to I less than 10 I plus plus, right? So this would be, we want to run through something 10 times. We'd start at 0 through 9, because that's going to be, the general case. And the moment that I equals 10, where I is no longer, goes beyond, when it goes beyond 9, that means don't run it anymore, right? So the first time in, we're going to initialize, this is our initialization phase, our check, and then after each iteration of the body of the for, we're going to run this kind of post phase here, which is going to be quite often, our increment of our value. Actually, if you say plus plus I or I plus plus, doesn't really matter at that point, because it just occurs at the end after your iteration to the loop here. You'll notice in this case, I haven't put any braces or curly braces around this, so it's only going to run the one statement directly after it, right? So there's the simplest scope here. Good practice might be to put our curly braces there, so that if we add any other code, more stuff, other stuff in the loop, right? Everything that's within that scope will get executed. If we accidentally get into a habit of thinking that if we've come from another language, yeah, this is a bug I see people do a lot, especially if they've come from a language where tab established scope, they might be thinking that this other stuff would happen in that loop because it was at that same indentation, and it won't. Right, so that's one thing to be really, really aware of. So you can do all kinds of clever things with your for piece. For example, if you wanted to emulate a while loop, you could just say, well, there's no initialization, there's no post piece, and you're just checking this condition. So just like we had that while is not dead, or whatever that was in our past one. Is it while is not dead? Or while is alive? We could have had that say, for is alive. And that would get us through there. You can get as fancy as you want in terms of that type of operation. So it doesn't have to be just the classic iteration inside a for loop. Right? A version of the for loop that you see a lot in game programming and in Unity and C# is this for each, which is specifically designed to allow you to iterate through members of a collection. And we'll talk about collections not today yet, as we're going to cover that in a future lecture. But the idea behind collections is, things like arrays or lists or dictionaries where you have a whole bunch of stuff, right? A whole bunch of things. You have a whole bunch of enemies in your scene, or a whole bunch of parts of a ship, or objects on a screen, and you say, okay, I want to have something happen across all of them, or I want to have some for loop that works across all of the elements of that class, the members of that collection. And for that, we'd use for each. So don't worry too much about the syntax at this point, but imagine we had a list of strings, right? So a whole bunch of different strings. They might contain people's names or something like that. And we wanted to perform an operation on each one of those strings. We might use this. We might say for each string, give it a temporary name to be used within this context. So we would say for each string p name in player names, which is the set. Right, so we have the element, or the momentary element, and within the set that we want to iterate, and then we could execute on each one of those. Let's see, I'm losing my microphone here. All right. So for each, when you want to iterate over a collection, for when you're iterating over anything or just want to use it as a loop. Now, within all of those types of loops, we might have the need to, say, break out of the loop, stop executing the loop, move on to the next element of the loop before doing some other things. Right? We may not necessarily want to run every part of the loop for every situation. So we have ways to control execution within the loop or through a particular iteration of the loop called break and continue. Break dumps execution out to the end of the loop. So if we want to stop, so for example, say we want to run through a list of numbers, and the moment we see a number equal to 12, we want to stop processing through the list. That's our first piece here. For each int foo in the list of numbers there, if the temporary reference we have there to whichever element we're iterating on at the moment, if it's equal to 12, we print that we found it, and we break, which means stop doing everything. Or, in the case of continue, we can do things to say, okay, stop doing the iteration that you're currently on, but continue parsing through the whole list. So in the second case, imagine you wanted to only parse through the odd numbers. So So you would say, well, okay, given some condition, we would say first for each. All right, that part looks the same. Then our conditional here is, for those, if you've never seen mod before, basically is a remainder. So we can say, okay, if we divide by 2 and there's no remainder, meaning that it's an even number, right? So if the number is even, we say continue, which means, okay, don't do this stuff, don't do the body of the loop from here on, and instead just go through the next iteration. Right? So you have a way of selectively executing the body of the loop according to some condition, or partially executing it if you wanted. Okay, so that's most of the sort of abstract pieces. And I think at this point, diving in, seeing real cases of use sooner is better than later. Sooner than later, yeah. So now we're going to kind of cross over a little bit into some more complex data types and how they might be used in our first game that we had, our simple room. And there are going to be some data types that are going to become sort of our bread and butter in Unity game programming or any kind of game programming. Obviously, we have numbers or scalars, right? Everyone's familiar with the term when I say what a scalar is, right? It just has, it's a magnitude of something, right? Some scale. So the amount of some quantity, the magnitude. If you want to know how far apart 2 points are, for example, the magnitude of that is the distance between them. So magnitude and distance are pretty much the same in terms of how we're going to consider them here, right? So often, though, if you want to know the difference between two things, just the overall distance between them isn't good enough. You want to know what their relationship is, right? Not just how far apart they are, but how do they relate to one another in terms of an offset or a direction, or now we're talking about spatial relationships. And a simple number, a simple one value isn't good enough for that. A scalar is great if you're just moving along a number line, you're one-dimensional, but games are seldom just one-dimensional. And instead, we're usually dealing in 2 or 3 dimensions. And so we have these handy things called vectors. And the word vector gets used an awful lot. Physics vectors versus vectors in C++, where you have list-like structures. Vectors versus matrices, so on and so on and so on. It gets a little bit fancy, but here we're going to be talking mostly about direction vectors, right? So a direction vector, a vector in our case, is a measurement of magnitude and direction. So if we're at a certain point and we add a vector to it, it's going to move us to some other point, right? We're going to move in a direction for a certain distance. Right? So by themselves, vectors have no notion of location, though. They are not positions. Right? Positions are, they are a particular, we use vectors to kind of often represent positions, but direction vectors are the kind of the purer form, right? If we said, well, there's an offset vector from the origin, and we make an assumption about that vector, saying, okay, that's a vector applied to the origin, then it can be a particular point, right? A point will have an x and a y, or an x and a y and a z, and a vector will also have an x and a y, or an x and a y and a z. But you have to think of them in the terms of vectors. Normally we think of those as offsets from something because they're directions. They're not necessarily a specific point in space unless you make some kind of assumption about where they started. So the notation is the same. Positions we declare as being vector 2 or vector 3, or if we have a direction vector, we declare as vector 2 or vector 3. So you do have to sort of be careful about that. Just be aware of that. As you get into more specific, lower level math involved in terms of vector and matrix multiplications and so on, and what it means to multiply a direction vector versus multiplying or transforming a point that gets a lot more specific, but worth knowing about in general. So we're going to use vectors to describe quantities like velocity, force, and in our case, offsets from other vectors in this first case. Right? So the simple thing is saying, okay, what is the relationship of this point in space to this other point in space, or this object's location and that object's location. So one of the main things we're doing in our room game is we're going to kind of provide feedback to the user based on what are they near, what are they far, what are the distances between objects. So vectors, once we have them, we have these direction vectors. They can be combined. We can do things like add forces, add velocities, add distances. So if we said, okay, I'm going to grab my little pen here. Say, okay, start here. That's my assumption. I say, okay, here's a vector, add a vector to that point, add another vector, add another vector, add another vector, and wind up here. That would be the same, that movement, as if I said, okay, add this vector, this vector, this vector, and this vector is basically, that's the same as that vector, right? You can add them. So you can combine vectors and have a single operation as a result of a collection of vectors like that. Positions, however, you can't combine them that same way. So if I had a point here and a point here, you can't add locations. That doesn't really make any sense. But you can add vectors to positions to get a new position. So a vector plus a position gives us a new position. A position plus a position just isn't anything. A vector plus a vector is another vector. So we can't add positions. However, we do have the opposite. We can subtract the two. If we have a position here and a position here, we can say, well, what is the vector in between them? And that is just basically the subtraction of the two. And that tells us, okay, the vector that would be necessary to move me from here to there. Right? So, a little funky, but you'll get the hang of it. Right? So they're a direction and a magnitude. Vector 2's are always x and y, or generally x and y, vector 3, x, y, z. It does sound a lot like a point if you assume the origin. That's basically what we're saying, right? A point is a vector assuming it originated at 0, assuming it came from the 0 origin. Movement consists of adding a vector to a position. It can happen over and over again incrementally and animated, or it can happen in just one big chunk if you want. So, pretty straightforward, hopefully. If we have 2 points and we subtract the two of them, we'll get that direction vector, which tells us how to get from one to the other, right? If we subtracted b from a, that tells us how to get from b to a. This is the vector that, as a result, this point here really has no relationship between the two other than when it's added to that first one, because that's really the movement there relies on that being, the starting position of it, right? The resulting vector points to the first term of the subtraction. So it's always pointing back, or it's pointing at A. If A was the thing you subtracted from, A is the thing you point at, or point to. Now, one of the cool things about languages and object-oriented languages and things you can build in, stuff like this, you can build in certain functionality into the variables and into other operations. And there are a bunch of different things built into vector operations. One of the most obvious being the need for, well, once we have a vector, can we just ask, what's its magnitude? What's your length? We can easily do that. So imagine we had a vector 2 called offset, which was just a vector with moving 1 in the x direction, 1 in the y direction. We can ask, what is its length? By saying offset dot magnitude. Right? When we have an object and we want to look at we want to dereference a method or a property, we use the dot operator there. So offset dot magnitude gives us the length, which is going to be 1.414. How does it do that? Good old Pythagorean theorem, pretty easy. I'm saying straightforward a lot. That's maybe my new favorite phrase. I don't know why it is. So the calculations underneath are pretty simple, but it's nice to have, of course, a shorthand to do it. Just say, okay, give me the magnitude. Knowing this, we can use this in all sorts of interesting ways. We can do things like change the magnitude. So say we have a car or a player that's moving in a certain direction. We want them to run, or we want them to stop, or we want them to slow down, we want them to speed up, we want them to teleport in that same direction, whatever it is. So maybe we're just interested in the direction, and we modify their magnitude somehow. Right? The easiest way to modify magnitude without changing direction is to scale it, multiply it up. So if we took a vector and we multiply it, we're just changing its length. So in this case, we said offset times 2, or offset equals offset times 2. Now our magnitude would be 2.828, and we would just move twice as far the moment we added that to any particular point, or we added added that to a point. So we're commonly doing things like scaling things, especially as we're talking about velocity, some sort of movement. We want to make something move faster or slower, and so on. Or we want to scale something, scale the size of an object. Right? Sometimes we don't want to scale the magnitude, though. Maybe we want to set the magnitude. We say, all right, we don't want to just allow you to go 10% faster. We want you to run at exactly 5 miles an hour, regardless of what direction you're in. So this generally relies on an extra step or two, and this intermediate use of a pure direction or a unit vector, right? How many, this is, well, unit vectors. Basically, we're taking the vector, forcing its length to be 1, and then scaling the unit vector version of that vector. So it's an easy way to say, all right, I want to preserve the direction by turning it into a uniform vector, right? Dividing it by its square of its magnitudes, a square of its components, and then using that, then scaling that end result. So you could easily set it to move at a rate of 1 or 2 or whatever it is in that same direction. All right. So, any questions on this piece? All right, that's going to end the review from last time and a couple of new things about our new best friends vectors and scalars and vectors and magnitudes and so on. So in our little test project that we had created a couple of buttons last time, and the buttons just moved us north and south. All right, everybody's here for that? And the way that the buttons worked is that we add buttons to the scene here. And let's see, canvas. So we added some buttons in. And the buttons were calling a routine inside of our Hello World component. One called North button. And on the south one, there's a south button. And they're referencing code that's on our game manager object. So if we look over here and we say, okay, let's look at the game manager. Game manager has this script on it called Hello World. You can double click on that. You can see here's this Hello World script. And it has a couple of things in it. The main things we had last time, where we had this hello button, which changed the text. This is a very fundamental piece, you'll remember. This idea of getting a game object by using its name, and then getting a component on that game object by using a generic function to ask for a specific type of component. Right, so we got the text component that's on the Hello World game object, and then we modified its text. Right, so that's our little hello button routine. And we also had north button and south button. And last time around, we created this player, which is a sort of a dummy object, actually. Right? It has no components on it other than its transform. Now, a transform has a vector 3, or a set of vector 3s, sort of. The one we're most interested in is vector 3 that represents the position, an x, a y, and a z value. And if we run the game, we had set it so that when we press the north button, we got a reference to that transform. Let's see, this one. Right, so the north button, for example, we got the vector 3 that was the position of the player. Right, we got the player object, and we looked at its transform position. That gave us that vector 3. We added one to its y, so we've moved it up on the screen, north. Right? And then we put it back again. We said, all right, change it. So the result was that in the game, if I, again, main camera, and I start pressing this, if all goes well, sorry, player, there we go, where's the player? Has already moved way up top there. Let's move him south again. Right, so the player is moving up and down because, you see over here, the y value is changing by fixed increments of 1 or decrements of 1, calling that. Right. Now, you might notice, in addition to that, over here you'll see score changed. And every time I'm clicking, this score is changing, or this text on here. And the text is, where is it here? This text on the canvas. So I threatened that I would show getters and setters, and that's sort of how that is happening. So let's look back in the code a bit. So the one additional thing I added is this check door here. And in check door, I said, okay, every time the player moves, I don't care if it's north or south, and eventually we'll add east and west, I want to check, is the player getting close to a door or to something in my game, right? That's the idea. One of the main things in these adventure games is I want to get out of the room, or I want to get the key first and then go out of the room. If I'm holding the key and I'm near the door, then I can get out of the room, that sort of thing. So as the player, every time the player moves, I call this function down here called check door. And check door is kind of a little bit boring. The main thing that we even see at this point, we don't see most of this, we just see this score plus plus. So every time, and it's more or less, these are turns. So every time the player moves, check door gets called, and the score is incremented by 1. And it also does some stuff here to say, okay, am I getting close to the door? Now, if you'll recall from where we were just a minute ago in the lecture, we have two positions. We have a position of the door. We have a position of the player. So we say, all right, let me figure out the vector between the two of them. Right? So I'm going to point from the player to the door. So I subtract the position of the door, or excuse me, I subtract the position of the player from the door. That gives me this target vector. And I compare the magnitude of that, I see, is it less than 2? So I wait until that magnitude is less than 2. And at the moment that it is less than 2, I can say, oh, okay, you're getting pretty close to the door. So right now, this is of not an awful lot of good use because I can only move in Y. And I'll fix my example, I guess. I broke my example before where here's the door, and the door is up here and to the right, and the player is down here, so there's no real way to get within 2 just using the normal interface we have right now. So let's cheat a little bit and we'll say, let's move this door to here, right? So we'll round it off, 3.5, and x is 0. Now you'll notice I can only increment by 1 in my movement. So if I compared to exactly the same here, I would never hit it. This is someone posted on one of the Unity forums the other day. I love these kind of questions. They're like, okay, wind up in this infinite loop because they compared something to explicitly say, is this the same as that? Is the distance 0? And in floating point math, and when you're incrementing by weird amounts and so on, you almost never wind up with like an exact number. So it's often better to look at, the magnitude is less than or is within a threshold, or within a certain value. So in here, I'm comparing to the moment that the distance between these two objects is, or the magnitude of the vector in between them is less than 2, I'm going to say I'm pretty close. So let's go ahead and check that. Let's see, save. And now for now, it's only going to show up in the console window, but let's go ahead and we see we immediately got pretty close, right? Because there's the player, or there's the door, there's the player, they're within 2 of one another, right? Notice it doesn't matter if I'm past it or before it, it doesn't care about the direction, it just cares about the magnitude, right? That's the other kind of cool thing about just working with magnitudes. It's an absolute. It doesn't know what direction the distance is, it just knows the magnitude of that distance, right? So let's leave our program there for now. Go ahead and save it. And I'm going to go ahead and at this point normally I'd want to go check all these things, check them in, make sure. I'm not going to do that. Just don't want to tempt fate at this moment. But. So let's go back over here and keep that in mind and see how much we can dive into here. All right. So let's talk more about Unity's UI and Canvas, and plus the basics of our one-room adventure. We can get to that. Now remember that the Canvas and UI are basically the player's heads-up display. They appear over the game, so none of the objects that we're placing other than the player and the door, those were things we placed as empty game objects. They were in the world, the game world there. The other ones were really just on this canvas, right? So they're overlaying the world. And my Iron Man cliche, or Iron Man example here, it's not Jarvis fancy or voice activated, but the concept is the same, right? They overlay the world, they overlay what we're looking at. You can get fancy. There are fancy ones like sliders and checkboxes and so on. So in project 1, we can't see the world, right? None of the game objects in the world have anything on them. We could, but we won't just yet, maybe. Maybe we'll add that, who knows. But we do have graphic controls and sound is the idea in the first one. So recommend using some of these, and this is like there's points for each one. How many points do you want to get, right? How many things you want to demonstrate? That's the way our sort of our accumulated point system works as opposed to our average grade system, right? We're working on accumulated points, so you want to demonstrate different techniques. So within the Unity UI, things that you might want to use in this particular project, obviously buttons and text. Toggles are really great because you have an on and an off state. So if you do things like, oh, I want to turn on a flashlight or have some resource that runs out after a certain time, toggles are really kind of fun to manage that sort of thing. I turn on my flashlight, I wander around with my flashlight, I turn off my flashlight, hit the toggle. Sliders are great for things like background music. Who doesn't like to turn down the background music when it's just too loud in your game? So useful for that. Maybe you have other sorts of text and so on. And then you probably want to have some audio sources in your game. If you want one-shot sounds or continuous sound effects, background music, that sort of thing, you'll need audio sources for that. And hopefully everyone has downloaded that lobby control, and we'll talk a little bit about scene management and how we can take advantage of that and do things like end the game by going to another scene, or start from the lobby and go to a scene, that sort of thing. So these are the main techniques, main objects that I'm kind of looking for. We've already attached methods from our controller or game manager script, or hello world just happened to be in this one. Maybe go back and rename hello world. I have to rename the file and the class to do it, but we've already attached certain methods from our game manager script to the on broadcasters of the UI buttons and toggles, or in this case we've just done the buttons so far. So when on click happened, I connected the north button and the south button to those things, right? So when I say I attached a method to a broadcaster, right, that particular object, when that thing happens, it broadcasts that occurrence to anything that's on that list. We'll talk more specifically about the broadcaster or the publisher subscriber pattern. Is anyone familiar with the publisher subscriber patterns? And anyone done like was it the Gang of Four, the game programming patterns? Familiar with that a little bit? Then there's a game programming version of that. It's kind of common things. So we'll look at a couple of those, and a lot of them, these programming patterns start in one discipline and wind up in another, so hopefully you'll find them useful wherever you wind up. But this is this notion of saying, okay, an event happens and other things need to be notified of that event. So we've already kind of dabbled into this sort of structure without really even knowing it. Right? We had our on-click or on-value changed. Now we did the on-click version in these buttons here, where here's an older version where, okay, the game manager object, or the manager game object, had a manager. Now we have hello world and game manager, and we just called a specific function. There are ways that you might, one second, just my sneeze, but I'm just getting a little fogged up underneath my mask here. Sorry about that. Subject anyone to that. So we've handled the basic case. Now what we're showing here is, in addition to that, we can do things like pass values into those routines based on the state of the UI. Right? Buttons are simple, like a button clicks, something should happen in response to a button. A more complex thing like a slider or a toggle, though, you want to know, well, what's the value of that toggle? What's the state of the UI? What is where on the slider is it currently at? Right. So there are ways in Unity to tackle that. Let's jump back over here and take a look. So let's add we'll add a toggle over here. UI, and this will be a toggle. And we'll put this down here. And we'll scale that. No, I guess I'm not really scaling that. Can I see it okay? Well, I guess you can kind of see it there. All right, so we have this toggle button now, and I'm going to change the label on that, the inspector, and we'll call this flashlight. And the toggle itself, you'll notice, is on. It's currently clicked here. Click that on or off, you'll see the checkbox turning on and off for that. So the idea would be, okay, how do we tell our program that that is on or off? So let's go back to the game manager, whereas for now, our first program is really going to should really just have one script where we're going to put all our code, right? It's just a game manager up there. We're not divvying out our functionality among lots of objects just yet. We're kind of old school here, kind of sort of old school. And we're going to create a function called public, and this be a void, and we'll call it flash on, or flash state. Flash. There we go. Now, because we know that we're going to be working with a toggle, and the toggle is either on or off, I already know one bit of important information, which is to say, well, chances are I might want it to pass a value in. Whereas last time I just had it call a function. The button was pressed, I just called the function. I didn't have any parameters passed to it. In this case, I'm going to say that I want to receive a Boolean value. And I can't just say, oh, give me, I can't arbitrarily say that. I know in the case of a toggle button that that is something that it will pass to me there. I'm really having trouble time today. There we go. So, and here I'm going to say value was val. Now, this is something I probably wouldn't do in a straight up C program. And in many others, it's going to be, it's doing a little bit of fun for me here, a little bit of lifting for me, in which case I'm trying to add a Boolean value here to this string, or this character array, even constant character array, before it gets printed. It's going to know how to convert that to a string for me, right? So don't be too put off by the fact that I'm adding a Boolean to a string here, which is a weird thing to do. The compiler is going to take care of that, convert things to a common agreeable format if it can, and it would hopefully do the right thing. So I'm going to save that code. Now the question is, when I come over here to Unity and I have that flashlight, and you'll see down here I have on value changed, not just on click, but the value changing. All right, so if I click on it and the value changes, things that are on that list will be called. So I'm going to tell it to go to the scene, and we're dealing, everything's on the game manager. And the function I'm going to call is, did I remember to set it? Did I remember to? Flash state, and you'll see it says bool, right? Now, if you are keen-eyed here, you'll notice I have flash state down here, which is passed a bool, and I have flash state up here, which is not passed anything. Now that's odd, or at least it seems odd by first. So if I just press flash state and I run, and I go ahead, and it seems to work. Right? Flash true, flash false. So I'm going to press it again. It's false now, and so on. Let's stop the game. So that one is this dynamic bool. Right? The dynamic variables up there, the dynamic things are things that are happening in the UI. So if there's a slider and a changed value, it would send me that new value. Not just the fact that it's a changed value, but actually send me that value. And here it's sending me the bool, the true or false. This other version down here, you may notice, now I have this box that showed up here. And I can decide to check that box or not check that box. And I'm now specifically sending it a value according to what I do here. So if I check this, and I press play, no matter what I do over here, it won't matter that the thing is actually on or off. It's always sending in that true value here. And if I set that to false, you'll see it is now always false. So it's a little bit tricky in that we have these two different versions, the dynamic and the static versions of those things. Generally, if you want to get information from the UI, you're going to wind up using that, the dynamic version. Okay. So let's leave that for the moment and then just say, okay, well, in our program, we'd be able to go from there and decide what should we do knowing the flashlight is on or off, right? Maybe we decide, okay, the player can see, so we'll give them information about if they're within 5 feet, if the distance is 5 feet away from the door, we tell them about it because the flashlight's turned on. Flashlight's turned off, they could walk right past the door. Right? We'd never tell them about it. So let's continue here for a bit. So UI elements, Unity's UI entities, are objects that own other components that contain properties and methods that can be accessed by others. It's the same thing throughout. They're just other components. There's a little bit of, common extra special, the special sauce of UI components. But we can consider them to be game objects and to have components on them. So therefore, we can find which game object, we can change the text on them. Like the first version, the first thing we did the other day was we said, okay, we wanted to change the text on a game object. We changed the text on a text object in the game. So we used the find to get the object, and then we found the component later on. Now in this case, there's a couple of different ways we can even do this. We can either find it explicitly using gameObject.find, or we can create a public reference and populate it using the Unity editor. Here we're getting into all this wonderful drag and drop versus scripted behavior sort of thing. Like, for example, if I look at the piece of script that is, I guess I should, here, I forgot, I got sidetracked. Score, how is score changing? Suddenly we have this text drawing on the screen here, even though all I'm doing is saying score plus plus. I didn't say, text score, whatever this, that, the other thing, anywhere. Did I? Or did I? I guess I did. But it didn't look like I did it here. I actually did it up here. And this is, I threatened talking about getters and setters, which, like I said, they feel like an advanced piece of language, but I think they're really, really useful for things like this. So I created a variable called score, or a property called score in my game, because that's, games have scores after all. And I could have just made that a public int or a private int and just said, okay, you just increment score every time. But instead, I've created this is defaulting to a private value called underscore score, right? And it's an integer, but it's a private integer with the name underscore score. And nobody touches underscore score except for this interface here that I've created, which I've defined it as looking like another int. It looks like an int called score, but if you try to set that value, which includes doing things like changing it and reassigning it, right? That's still a set. So if I would get the value, do something to it, and then set it, right? That's always, there's assignment is part of what's going on. So there's a get and a set. So as part of setting it, if you change it, if you said plus plus, you just added one to it, what it would do is say, okay, here's the value that you just asked me to put into it. And so now I would say, all right, I'm going to go ahead, put that value into my storage here, and additionally execute this line, which changes the text of this game object called feedback text. It gets the component and sets its text to that. So anywhere in my code that I just say something like score plus equals 12, or score plus plus, or score minus 4, or equal, wherever, whenever I change the value of score, it will automatically fix that. It'll automatically update that. Right? Nice. So I don't have to, every time I modify score, I could make a function or another method that did that, but I can make it look like normal syntax. So it just looks like score plus plus, or score plus equals, or whatever. Now the other piece that I wanted to talk about is this part here where I said, okay, this text, the game object that this text is on is this thing called feedback text. So where did that come from? How did I get the reference to that? In other places, I would do things like this. I would have said GameObject.find, but I didn't do GameObject.find my text object here. Instead, I declared a reference to a public game object called feedback text. So that can be named anything, just as long as it's, whatever it is consistent within the scope here. And rather than set that via script, I set that in the Unity interface. So if I find my game manager, you'll see now it has a public reference to this feedback text. And this is, have to warn you, one thing that Unity does. I don't know why they haven't changed this. I can't think of any good reason for this. They do this for readability, I guess. That's their reason. You'll see this, it's referred to as feedback text. I put a space in the name as a favor. It did me that favor. I didn't name it feedback. I named it feedback text, all one word. But it wanted it to show up cool in the interface like that. So that's one thing it does. When things show up in Unity's UI, it does that. But now, the important part was that I could say, all right, this text up here, which is, which text is it? If I click this one up here, I'm going to go down here, Game Manager, and for the moment, here's another pro tip. See the little lock up here in the upper right corner? If I'm going to be modifying something about this object, and I need to get a reference to another object, or drag and drop it, I might want to lock this. Right? If I lock this, now this isn't going to change depending on what I can switch to other things in this here, and that doesn't change. That's handy for when I'm saying, all right, I want to drag this over to here, right? So let's do something just to be clever, and we'll say UI text, and this one we'll have down here, but I'll drag that and put that there, and press play. And now you'll see this bottom one is changing, right? Because I changed that reference by dragging this one on. Might be a good idea to start naming things, right? This is usually where you suddenly realize to yourself, you say, oh my God, I've got a whole bunch of things named text in there, and I can't tell which one is which. And I certainly can't tell from here which one of these text fields is actually being updated, right? So now might have been a good time to say, well, let's rename this one now. Before I do that, I want to undo that. And we'll call this one small text. Now the good news is, if I come over here, you'll see it's already changed small text for me over there. So Unity does me all kinds of little favors like this. And this one up here I'll call big text, because that's super obvious. And we'll go back to Game Manager. Whoop, not that. That. And we'll tell it, yeah, update big text. And away we go. Everything's working. So we could use GameObject.find, we could use drag and drop in the Unity editor, different ways of finding references to Unity objects so that we can modify them. Right? So we did those two methods there. So once you have a reference to an object, you can get references to its components. Done that. Get component text, for example, right? So if you need just a once off, you can, this is doing it plain it out, spelling it all out like that. I mentioned it's not super efficient, especially this part here, right? Because it's going to search through all of the objects in your scene until it finds one called foo, or whatever. So it's not great to be doing that all over the place. Better to take some reference, right? Do your finding all at once in the start, and then use references in the scene. Right? So for example, like this, I might specifically define a variable called textcomp as text, did this whole step inside of start, and then every time I want to change it, I can just say, oh, textcomp.text, textcomp.text, whatever, change it there. Way more efficient. I've avoided that whole hashing of the whole hierarchy. You can do clever things. \n, we didn't really talk about that much, new line. Let's have new line, carriage return, line feed. But you can hard code, embed in new lines into text. So if you wanted to do things like have a big box of text and you wanted to split it at certain intervals or certain, rather than just having it wrap, you can embed new lines in your text there. Pretty easy to get text boxes to say what you want them to say. Right. Now, remember our checkbox, our toggle. There are other things other than just the text. Now, maybe you want to set the toggle to something, right? You don't want to just let the user click on it. Because you might say, well, okay, the user tried to click on turning on the flashlight, but the battery's dead. Right? So we have to have some way that's not good enough to just let the user click on that field and say, yeah, I can turn the flashlight on all the time. You might say, oh, the user tried to turn the flashlight on, but I compared it to the number of charges left of batteries, and therefore, if battery charges was 0, I would say, nope, set is on to false. Right, no good. There are no more batteries, so even though you just tried to change it, I'm going to set it to false. This is also useful for, say, at the beginning of the game, we're entering a scene where maybe you don't know, does the user have a flashlight on or not, and you want it to be reflected in the user interface correctly, right? So inside your start routine or something, you might say, oh, let me set the flashlight to the fact that it's turned off, right? Or you want to disable some button, right? You can always get at these other methods, these other properties and fields, just like we got text. And there's lots of other components as well. If you want to get fancy, we have things like images, which are not really required in the first version. And images have sprites, which are basically bitmaps that you can pull from other areas. We'll get into that. We have the text component. That one is a favorite. This is pulled from an older Mac interface. My apologies for that. But things you can change. You can, even on the fly, you can just say, oh, okay, this text should be blue because that's what suits the narrative. We can change the size of the text. We might animate the text. We might animate the fact that it's going to be transparent. We'll do that later on, things like that. Buttons, we have their events, and we have their images, and so on. Lots and lots of different things. We're mostly going to be dealing with text and buttons here. You notice that there are certain things that they share, their names, where they're enabled, the game object that they're associated with. They might have tags on them, and so on and so on. We can color things. Another one of our it's like a vector, but we can have colors which are made of like red, green, and blue components, just like positions of X, Y, and Z components. So we have some predefined colors even. We have color.blue, color.white, color.red, all the kind of the primaries. We can also specifically say what color we want things. Red, green, and blue, right? Mixes of red, green, and blue. Values between 0 and 1. So if we want something pure blue, that first one is the same thing as saying color.blue because it has a 1 for the blue component, red, green, blue. There is a fourth component to color, which is alpha or transparency. As we get into things where, okay, can you see through this? Can you see other objects underneath it? Right, so you have whether a color or a pixel is, how transparent is it? So color science in Unity is largely just RGBA, red, green, blue, and an alpha value or transparency value. You can use color 32 if you want to say, oh, I'm working in 32-bit color. You can do that if you want to be that specific about things, but generally just working with colors is fine. Right? All the same thing here. Color blue, blue, opaque blue in 32 bits. All the same thing. So hopefully, I'm going to use this as an example, as a exercise. You can, the exercise, the practice is to go ahead, start building your user interface. Start doing things like, positioning your buttons, your 4 directional pad things, your toggle, your setup. Do a bit of designing before this game. This game is definitely meant to go together quickly, but sketch it out. Do you want to have, for purposes of your game, is it okay to have just one big text box where you're telling the story, or do you want to have some kind of constant, constant feedback regarding warmer, colder, so on, and then you have the story down here, and you have 4 pads, or is your managed resource something that's an instantaneous, like flash of a, ping of radar, or a flash of a camera, or is it a flashlight you turn on and off with a toggle? Think a little bit about the design, and then sketch out what your interface might be. All right. So, sorry again. It's overheating under this mask. Humidity, it's real. All right. So I want to cover just the basics of, let's see. I should keep a clock. Okay, my watch is right. That's where my watch is running down. So scenes, right? So everything, we're working within a given scene, and we have the canvas in our certain scene here. But I want to do sort of a whirlwind tour, especially because we talked about the lobby, and we want the lobby has 4 buttons, and from those 4 buttons we can kind of go to other scenes. How does that work? We have a namespace. Now in C# we have a namespace just like other languages where we say, okay, if we're working within here, we have a default namespace, or we might have using a certain namespace to say, okay, what set of objects we're working with. But the scene manager is within unity.scene management. So if you want to use it in your in a particular file, particular script, you want to say using Unity engine.scene management. It's not included in everything. The assumption is not all components need to know about scenes. Certain things where it says, okay, not everybody needs to know about UI elements. Not everyone needs to know about scene management. But if you're defining a component, everybody needs to know about certain component things. So sometimes you need to explicitly say using what namespace. So we say using Unity engine.scene management, sort of like an include. Then we're free to start using our scene manager functions. The basics of scene management, right? You have this hierarchy we saw in the Unity interface. Everything that we're currently working with is in a scene. And you load a scene. You want to change from one scene to another. You can think of it as, well, maybe I have a level in my game. I want to move to the next level, so I load that scene. In the basic case, you have load scene, and you can refer to a named scene with a, in quotes here, a string. Or you have a scene index that you can refer to. Or you can even do things like getting the active scene and the build index off of it, things like that. You get fancy. For now, we want to do just the basics. Loading a scene as a complete unit synchronously. What I mean by that is when you load a scene, everything in the current scene goes away unless you're explicitly asking it to, and we'll eventually get to that. And you build, so it tears down the current scene and instantiates the new scene, right? Swaps out the old scene for the new scene. It's one way to do it. It can be far more elaborate than that. We can have it kind of dynamically or asynchronously load pieces of scenes into other scenes. So as you wander around a world, maybe you kind of do the Minecraft thing where suddenly more parts of the world come in as you get near them, and parts get unloaded from the world as you move away from them. You certainly can do that. But for now, the simplest case is we tear down the current scene, we load a new scene. And certainly with regards to our lobby manager, that's kind of what's going on. So if we look in here, and in our project scenes, you'll see we had a main menu. Let's save that scene. It always asks about scenes. Within the main menu, the main scene here, each of these buttons calls a function on an object called scene loader. So this, you see this object here called scene loader. And that scene loader instantiates this class, this load a scene class. And it's really, really, really simple. In fact, all this class knows how to do is load a scene by name, so it's change scene, or you can call return to main, in which case it just says, okay, go back to the main menu, go back to the main scene. Right. Now this is one of those cases where, remember, pay no attention to the static piece of it. That was a test, and that should have gone away. My apologies for that. So this, if we looked at this and said public void change scene, scene manager load scene, okay, there's the name, the string name. Now let's look at where this is called. We'll see it actually called here, say on adventure. And we say it's on that object. The thing we're calling is change scene, passing it a string. It's not a dynamic version because it doesn't really know, we don't have a string that we can pass into it, but we can right here give it that string. So each of these buttons in our scene here calls the scene loader object change scene function or method, and it just passes it the name of the scene it wants to load. And then if we go to one of those scenes, and some of them are broken at this point, I'll leave it to you to fix. If we go to adventure, for example, you'll see it does have a button down here called return to main menu. And return to main menu, now we had to have the load a scene script instantiated somewhere in the scene so it would know how to get to that. So it happens to have that script on it here. And it says, okay, use the load a scene return to main from here to get back to the other one. All right, so it's really, really, really simple main kind of scene management. So let's try to make it work. I hit play, and I'm in my current scene. Things seem to be all in place, so I should be able to say return to main menu. If I click on return to main menu, nothing happens. That's not entirely true. If I go over to the console, I'll see that something happened, which is that it complained. It said main menu couldn't be loaded because it has not been added to the build settings, or the asset bundle has not been loaded. To add a scene to the build settings, use menu file build settings. So you can have tons and tons and tons and tons and tons of scenes in your project. That doesn't mean they're going to be all accessible all the time. You can go to them and launch that scene in the editor, but when it comes time to actually build your game, you're going to have to say which scenes really are there. Right? This is nice so that you can sandbox all kinds of different things in the same project, but in the end of the day, or when it's time to publish, you can say, okay, I want this scene, and this scene. So that's what leads to this error message, though. So we need to fix that. We need to know about this build settings. Click on build settings, and you'll see right now it only includes sample scene in the build, which is, of course, no good. So what we want to do is come down to the project here and say, well, include adventure, include main menu, include apple tree and platformer, and shoot 'em up. And actually, we're not going to include sample scene. So at the end of the day, we're going to say, okay, these are the ones we're going to start off with. You can also notice that I can move them around. And you'll notice these numbers, 0 through 4 over here. Those are those indexes. So you can load scene by index, or you can load scene by its name. So once it's there, once it's in the build, even though I'm not going to build it here, I'm just going to put it in the build. Now it knows about those scenes. So while something is running, I can say return to main, and I can get there. All right, I can go back, adventure, get back there. All right, that's the important part. That's the gist of scenes for a while. So we'll pause our scene discussion there. And we'll talk about audio for a bit. Did you hear that ping? So audio sources are pretty straightforward. We want to include those in our project right away. And the simplest way to add audio to a scene is just drag an audio clip into the scene. An audio clip can be any WAV file. MP3 files work as well. There's lots of sources. You can record your own, make your own sound effects, whatever you want to do. Record a barking dog. A great application for editing them is, why am I suddenly blanking on, I can picture it running on, I don't think I have it installed in this. I'll think of it eventually, but you can use any sort of audio application, any recorder. If you want to actually edit sounds, that's where you need to kind of get fancy. If you want to like shorten things, cut out dead space, things like that. But it's really easy to incorporate audio, find stuff, royalty-free loops, whatever you want to do, and incorporate that into your game in one way or another. And it's as simple as dragging the audio clip into the scene. That will create an object with an audio component already on it, ready to go. You can add audio sources to other objects, which is, in the long run, the preferred way to do it, right? You think about an object, a car, or something, the car should make its own noise. You hit a wall, the wall should make its own noise. Yeah, that sort of thing, right? Objects should take responsibility for making their own sounds, and it's a great way to organize things. But for now, we might just say, well, all right, we could drag a bunch of sounds into the game to make life easier and change their properties in the editor or through script. One of the main things to think about, play on awake is something that gets people right away. Play on awake just means as soon as the game starts playing, play this sound. So if you dragged a sound into your game and play on awake was set, it will play it immediately. So here I had some sound effects, and let's specifically drag this ping into the scene, and I just drop it somewhere. I dropped it at some random crazy location. I'm going to put it at 0, 0, 0, just so that I don't lose track of it. Notice it says play on awake. It doesn't say loop. And if all goes well, for some reason the sound isn't working today. Went to hell, but well, normally it would immediately play the ping sound. I'll get that squared away before tomorrow. If you don't want something to play the sound immediately because you don't want, it's not a background sound, it might be something that the moment you hit a wall, thud, then you should play it. You turn this off so it doesn't play immediately. So if you have a bunch of sound effects like a yay sound, a dope, which is the thud against the wall sound, the ping for radar, and the background music, you might drag those all into the scene and set them all their play on awake to false, for starters. All right, so I'll do that. Drag them all in here. Try to do it. What's going on here? And there. All at random, stupid locations. And I should go through, make sure they're not all play on awake. Except for maybe the background music. If I want the background music to play immediately, I'd say play on awake. And I could also say loop, to just play over and over and over again. So if everything was working correctly, I would just hear the sound. Or is that? It's not a great interface. I think that's not a, is that on or is it off? Is that what happened? Let's go back to Que Sera Sera in the scene here. Play on awake and loop. Nope, not that simple. All right. So now I have those audio sources, and then I could refer to them. I could play their audio objects if I need to then, right? Let's get this here. So we have two basic types of sounds in games normally. We have this sort of one shot where we'd use the play, right? So we get a reference to the audio source and say audio source dot play, and that would play the sound through to the end. Generally, of course, you want it to set the state so it doesn't play on awake and it doesn't loop so that you can control. So in this case like here, maybe I have it say, if the health is less than 2, I play the groan sound. If I bump into the wall, I hit the bump sound, that sort of thing. Right, we're straightforward. Here, I did it again, straightforward. Okay, so now we have much of the game objects that we'll need for the game. We'll talk a little bit more about the whole 2D space. And how's everybody doing? Is everybody okay? We're good? We're still not falling off the end of the day? All right, let's see how far we get. So our game is going to be 2D for now, and most of the games we're going to deal with are going to be 2D. We'll see where we wind up with. But let's conceptualize the whole 2D. So the position is encapsulated in our x and y, right? We know where we are in the scene, where we are in the world by our x and a y. We have distances, which are one-dimensional, which tell us how far things are potentially apart. We've already seen the true and awesome implications, the powers of vectors, so we're ahead of ourselves a little bit. But we're thinking in terms of positions and distances, and you already know some of the underlying stuff because I introduced that earlier in this case. Now, one of the big things we're going to do in this game, we're doing something that's kind of brute force. So later on in the game engine, we're going to allow it to do all of our collision detection for us and to kind of keep us in a scene or let us bump into objects and things in far more elaborate ways. But for now, since we're doing it the old school way, we're going to figure out, are we allowed to bump into walls? What happens when we bump into a wall? How do we even tell the player that they bumped into a wall? How do we prevent them from moving in certain ways? So one of the main ways to do that is just basically compare the player's location to see if it exceeds some boundary. And the moment it does, you kind of push them back in, and maybe you play a sound. Maybe you tell them, in this case. So imagine we have two vector 2 fields. In this case, this particular approach, and there's lots of different ways to approach this. I like this one because it's we set an upper left and a lower right corner on the screen. So we want to just say, okay, we're establishing rooms. They're going to be rectangular. They're going to be aligned with our axes. They're really, really simple. So we have an upper left and a lower right, and basically they're going to be corners. Yeah, did I mess this up? I should have edited this. All right, it's going to be up to you to get this right. So the idea is simpler though, or is similar. So the idea is that we're going to establish two corners. They're just going to be positions. They have an x and y value. And the player, we want to keep the player somehow in between, right? So we want to have a lower limit of x and an upper limit of x, a lower limit of y, an upper limit of y. And we want to keep the player in between, right? So somewhere early on in the game, in the start perhaps, or maybe even we make these public so that you can see them in the interface, you have your two corners. And we establish where they are. Now, -4 to -4, one of them should probably be +4 and +4 to say, you're within these values. And then you just compare. You say, if the player's position exceeds the upper left value, or it is lower than the lower right value, that means they've probably gone off the screen somehow. Or Now these are ORs here, double bar for OR in C#. If we were doing bitwise OR, which is a special case, we'll see in some usefulness to it. But for now, in terms of our logic here, we're saying, okay, player position greater than we're comparing the y values, and this is all part of this compound statement here where we're checking, is this true, or is this true, or is this true, or is this true? So if the user has exceeded the bounds in any of those 4 instances, in those 4 cases, then we can set the feedback text to like, you hit a wall. Important thing about this, though, we didn't prevent them from moving outside. We just said you hit the wall. So the next step would be, of course, to say, well, what do we want to do? We could step in and say, player position dot y equals, or clamp it, or do something to say, don't let them go outside of that. Right? So this is the simple case. In position 0, 0, is position 0, 0 inside the rectangle defined by the corners? Sure. How about these other numbers? Right? This is the basics of box collision, or axis-aligned boundary boxes. If you get into computer game architecture, or you get into computer graphics and so on, you'll get way more in depth on this sort of thing. But the basic idea is that you have some sort of box that's defined that is aligned with your axes, so it's a simple case. You just see, is that point within those other corners? Right. So it's pretty straightforward. All right. If you don't want the player to move outside of there, we have to do something about it. And now we're going to use a library, potentially, a math library, a floating point math library, which is why it's called mathf. It's going to provide certain functions for us, and the one we're interested in is clamp. What clamp means is don't let it go outside this range. How many of you have encountered clamp before? Anybody? No? All right. It's very useful. It says, okay, if you exceed the lower bound, you get the lower bound. If you exceed the upper bound, you get the upper bound. Forces you in that space, right? Clamps your movement. Doesn't allow you to get outside there. It says, exceed a value, you get the maximum. So we can say player X has to be in this range. So in order to do that, we pass the value that came in, and we pass in the boundaries, and it gives us either the player's position or the upper or lower boundary, depending on if it exceeded or was lower than that. Right. Clamp keeps the value within range. This is provided as part of mathf, our floating point math library. There are other functions too, but clamp is what we need for now. All right. Distance. What more can I say? Good old Pythagoras. So if we have a vector 2, we have an x and a y. We have, you can imagine we can use x and y as a and b. We can square them. We can get the length of the hypotenuse, which is, of course, our distance from one corner to the other. So now we have distance. Math f is not what we use for that, because we want to be dealing with vectors. Right? Math is a scalar library. Right? It's just one-dimensional values. If we want to start working in 2 dimensions or higher, we can actually say vector2.distance as opposed to mathf.clamp. Right? There's certain libraries that belong to certain types of data depending on how we want to do things. Another cool collider, in some ways it's even easier. So imagine you want to say keep the player inside of a circle. Here, it's a matter of kind of circular collisions. One circle might be very, very, very small, which might be the player. The other one might be some large, so maybe it's the room. And here, it's just a matter of the distance. You don't have the corners to worry about. You just have to say you have the center of the circle and some position. And we can say, what's the distance between those two things? The moment you're far enough away from the circle, you know you're not in that circle, right? Your distance from the center of the circle tells you. Did you exceed that? Really, really straightforward. Stop saying straightforward. Whew. So, determining a point inside or outside of a circle is just a matter of the distance, and we can extend that to not just be a point in a circle, say, okay, two circles, do they collide with one another? All we have to do is add their radiuses, I can never pronounce that, their radiuses together for the check, right? So we add the two, and if the distance between those two exceeds those two radiuses, we know they touch or they don't touch. So from this, it's easy enough to figure out, are you inside the circle or you're outside the circle? Congratulations, now we've got intersection with squares, intersection with circles. So imagine you have an enemy, a werewolf, a thing, something you want to pick up, a bucket of water, a key, a large object. Makes sense to use something like this for whether you're colliding versus are you trying to stay inside a room, which is a rectangle. Then you start using, the kind of bounding box methods. Now, you can get fancier and say, all right, well, maybe my room is shaped like this. I don't know what this is going to be shaped like. It's like a gun. I should have made it Mickey Mouse or something. Yeah, let's do Mickey Mouse. Well, Mickey Mouse doesn't have any squares. It's a matter then of saying, well, my room isn't just one thing. My room is a compound shape. I can compare against all of those colliders, see which one, are they all true? Then you're there. Are they all false? Obviously you're not, right? So you can create this sort of notion of compound colliders. We'll see that as we get into tile maps and so on. Don't worry about that. We want to keep it simple at this point. So probably just want a square room with circular items that you can collide with. But you can get fancier than that if you like. We want the game to be more than just finding your way out. Maybe you have to find a certain point on the rectangle, certain location. And you can use a combination of this. Like you might say, all right, here's that rectangle, and simplest case is you say the door is here, and you just collide with a circle for the door and say, okay, you're at the door, right? That's sort of the simple version of the game. So for objects we're interested in colliding with, we do that. But we don't just want to say, okay, wander around until you bump into walls or get out. You want some kind of state, what's going on in the game, what's in the world, right? The player's position, the world's corners. These would all be properties or variables or fields, however you want to refer to them, inside, this is the game manager script. It's our one script, so we'll have those all as properties of our game manager class. You might have, is the flashlight turned on? How many charges are left of the battery? What is the current score? How many steps has the player taken? What's the player's health? What's the position of goal number 1? Maybe even more complicated things. Was goal 1 found? Was the key found? Was the window opened? Right? So as you encounter things, you say, okay, they've bumped into this, you tell them that. They say, all right, you found the key. All right, now we have to keep track of that. So we have to have a variable in our class that says key found or obstacle active. Did you have the key when you ran into, or did you have the sword when you encountered the basilisk? Or the mirror to look at, so you can get turned to stone. I don't know. But it's more now having things in the state of the game and managing what happens as you move around. Sometimes you're carrying things. Is this true? Is this false? Have you already encountered that? So you're maintaining some state in your class there. And with that data, now we're doing the things like sensing the world. Right? You can get far fancier. You could say, okay, I can collide, I have a circle around me that tells me That I can see if the flashlight is turned on, I can see the fact that there's a wall over here, or the monster is over there, or something like that, right? It doesn't necessarily have to be binary in that case as well. You can do things like say, oh, okay, dim lighting at 5 feet, or bright lighting up to 10 feet, dim lighting at 20 feet. You know, if you've ever played a lot of games, they have situations like that. Or you might even, it doesn't have to be about sight either. You might say, oh, okay, I can hear things within a certain range. I can smell things within a certain range. Right? This is the basics of kind of setting up sensory inputs to this. All right, we define what is their range, and then ultimately what information we're going to tell them. All right, we're running out of time. So think about that. We'll pick up there tomorrow. Right? We're done? Sorry, right up to the wire. But this should give you plenty of food for thought in terms of designing your game. So the homework for tonight would be, or the informal homework for tonight, or really just if you haven't already set up your project, shared it, invited me via email to be part of the project. Do that part first, worry about organization second. Make sure that, and think about some scenarios that you want to put into your game. Challenge yourself to do it. You have to tell the story. It should have a little bit of a narrative to it. It doesn't have to be epic. It should be something that can be conquered in just a few minutes. It doesn't have to be, like I said, not epic. Makes grading it that much more straightforward. And jot down some things. Jot down your map. Get out the graph paper if you have such a thing. That sort of stuff. See you tomorrow. Thanks for your attention. And remind you, if you ever need to interrupt me, just go right ahead. Otherwise, I'll just talk and talk and talk.